Hey everyone, my name is Taylor Sparks. I'm the editor-in-chief of Integrating Materials and Manufacturing Innovation, and we have a new paper to talk about. This one is about a benchmark data set for wire arc additive manufacturing, and the authors here come from a variety of institutes. You've got UC Davis, Sandia National Lab, Oak Ridge National Lab, and Iowa State. Lead author Nicholas Bachus, corresponding author Brad Boyce. This paper asks a relatively straightforward question. How good are our simulations of metal additive manufacturing? Are they good enough to predict temperature? Are they good enough to predict warpage? Are they good enough to predict the residual stress? And in this benchmarking study, they have answers to those questions. Let's dive into it. Okay, maybe first off, we can begin with the actual test, right? They come up with two different bars. They've got a calibration bar, and then they have a challenge bar. These are additively manufactured with the idea that they're going to deform, right? You see this sort of curl bar geometry. And since this is a benchmark data set, the idea is pretty simple. You're going to give researchers all of the information about the calibration sample. But you're then going to ask them to predict the behavior of the challenge bar sample, which is going to be much more challenging. And that's really what we do in industry. We train off of one thing, and we hope that our approach generalizes to new problems that they'll actually be useful for. The data set that they've collected for this is actually pretty robust. Obviously, they have things like the geometry of the part and the tool path. It also has validation data like the thermal history and the distortion measurements, which are pretty standard and easy to collect, but also has much harder to collect data, for example, the residual stress maps, making this what I think is an unusually complete validation resource for the community. We'll jump down here to the calibration object toolpath just to illustrate the difference between the calibration specimen and the challenge specimen. They're not just different geometries, they're different tool paths, and that makes a big difference. For example, in this calibration toolpath example, the torch travels really long distances between when it returns back to its original location. However, in the challenge specimen, that toolpath was much shorter, and it produced dramatically different thermal accumulation and cooling behavior. And that's important because we know that residual stress should be highly sensitive to thermal history, and we've changed it. So by changing the toolpath, the researchers here have created what is going to be a much more challenging test for predictive models. So let's jump down and see how we do. They are not the same, right? You see greater distortion in the calibration sample as opposed to the challenge sample. The reason for that, again, is because you have these larger distortions because there's stress accumulation along this long axis of the part. What I think is generally impressive here is that the predictive models were able to predict warpage distortion pretty reasonably. One model was within about 7% of the measured distortion, which at first glance seems like great, a real success story. But then we get to the real challenge if we scroll down to the residual stress plots. Yeah, so down here we see the residual stress comparisons. They actually measured the residual stress experimentally, and they did so with two different approaches. One was using neutron diffraction, and the other was using the contour method. So you can see the CM and the ND data points here. And those both agreed with each other pretty well, which is good. That gives us confidence in the experimental ability to measure residual stress. But our models for predicting residual stress really kind of fall apart. One of them actually predicted stress of the wrong sign, suggesting that it was compressive when it was actually tensile. Another one over-predicted the stress by a factor of 4 or 5 times. So in other words, even though our models can predict the temperature and the distortion relatively well, they are not doing a good job of predicting the residual stress. And that may be really important depending on the application of your wire arc additively manufactured part. And maybe that's the big takeaway from this study is that in the past we've relied on things like temperature and warpage, which provide sort of useful validation metrics, but they clearly don't tell the whole story because at least one important metric is this residual stress, and it seems to be the true discriminator between better and worse models, right? And if you're getting your model right in temperature and warpage, you might still be getting it wrong in terms of stress. The authors point out some of the reasons why that might be. Phase transformations, transformation-induced plasticity, constitutive behavior, or even incorrect boundary condition assumptions. But the point is, now they've actually created a resource that the community can use. Let's check it out. Here in the data availability, they show where you can actually access this data. And the hope is that people in the community will actually build on this, using this resource to make even better models to move the field forward. I hope you'll read all about it in the latest issue of IMMI.